The cosmos was once smaller than an atom. In the hidden history of the universe's first seconds after the Big Bang, a drama unfolded that made your existence possible. By the end of this journey, you will understand how the fundamental forces and the very atoms in your body were forged in a fleeting, fiery instant. We will uncover why matter exists at all and what triggered the universe's explosive birth. What single question about our cosmic origin feels most profound to you? This starting point defies everything we experience. A singularity is not merely a dense object. It is a state where all the energy and matter that would ever exist was compressed into a point with no volume at all. Infinite density, infinite temperature. In such a condition, the very fabric of space and time as described by Einstein's theory of general relativity ceases to have any meaning. There is no before because time itself did not exist. There is no place because space was contained within that point. Renowned physicist Stephen Hawking likened it to asking what is south of the South Pole. The question itself loses its footing. Our current laws of physics, which govern everything from falling apples to orbiting planets, simply break down at this precipice. They offer a prediction of this initial state but then fall silent, unable to describe the mechanics of the singularity itself. This is the ultimate frontier of our knowledge. The greatest mystery is what triggered the expansion from this incomprehensible state. What was the first cause that set the cosmic clock ticking? This question is the driving force behind the quest for a theory of quantum gravity, a framework that could unite the vast cosmic scale of general relativity with the bizarre, probabilistic world of the ultra-small quantum realm. It is a puzzle that may hold the key to our very existence, for within that unknowable singularity, the entire future of the cosmos, every galaxy, star, and planet was encoded, waiting for a single, cataclysmic moment of release. Out of the singularity's silent reign, the first tick of time ignited an era of such profound strangeness that our language struggles to capture it. We call this the Planck Epoch, a span so brief it defies human intuition. From the very first moment to 10 million trillion trillionths of a second later, the entire cosmos existed on a scale defined by nature's smallest possible measurements. Here, the universe was a quantum gravitational world, a domain where the four fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, were seamlessly woven into one single, unified power. Visualize the fabric of reality not as the smooth, predictable stage of Einstein's cosmos, but as a turbulent, frothing ocean. This is the concept of quantum foam, a vision from physicist John Wheeler where space-time itself churned with violent, unpredictable fluctuations. Tiny wormholes might have blinked in and out of existence, and the very concepts of before and after lost their anchor. This was a sea of pure potential, where particle-antiparticle pairs spontaneously erupted from the immense energy density, only to vanish back into the frenzy almost instantly. Our current laws of physics, the very tools we use to understand the cosmos, simply cannot penetrate this epoch. It remains the ultimate barrier, a curtain drawn across the universe's first act. The quest to lift that curtain drives the most ambitious theories today, from the tiny vibrating strings of string theory to the woven loops of space-time in loop quantum gravity. Then, in a pivotal shift, this unified superforce could no longer hold its form. The Planck Epoch ended as gravity peeled away, becoming distinct for the very first time. This first great separation set the cosmic stage, initiating a chain reaction of transformations that would ultimately build the world we see around us. The cosmos was not yet a second old, but its story was already accelerating. With gravity now charting its own course, a new era of profound unity dawned. From 10 to the negative 43 seconds to 10 to the negative 36 seconds, the universe entered the grand unification epoch. In this unimaginably hot and dense state, three of nature's fundamental forces were still fused into one magnificent superforce. The strong nuclear force that binds atomic nuclei, the weak nuclear force responsible for radioactive decay, and the electromagnetic force that governs light and chemistry were all indistinguishable. They operated under a single, elegant set of rules, a state of perfect symmetry that particle physicists dream of recreating. Think of it as a cosmic soup so primordial that the very ingredients of matter had not yet decided what they would be. The particles we know today as quarks, the building blocks of protons and neutrons and leptons, the family that includes electrons, were all the same. They were interchangeable, their future identities not yet written. This concept of a grand unified force is not just speculation. The work of Nobel laureates like Abdus Salam, who successfully unified the electromagnetic and weak forces, shows us that such mergers are not only possible, but are a fundamental feature of our universe's history. His breakthrough gives us a tantalizing glimpse into this far more ancient and profound unity. Within this seething, symmetric soup, the first true fundamental particles flickered into a ghostly existence. Borrowing energy from the universe itself, particle and antiparticle pairs would spontaneously burst into being, only to annihilate each other an instant later in a flash of energy. It was a chaotic, boiling quantum foam, but beneath the chaos lay a deep and beautiful order, and within that quantum frenzy, a tiny seed was planted. A random fluctuation, a patch of space with a slightly different energy density, began to gain potential. This minuscule irregularity was the trigger for what would come next, a quantum spark that would ignite the most dramatic expansion in the history of everything. The universe was poised on the edge of a transformation so violent it would stretch the fabric of reality itself. That quantum spark ignited a firestorm of creation. At around 10 to the negative 36 seconds, the unified force could no longer hold its perfect symmetry. The universe underwent a dramatic phase transition, like supercooled water instantly flash freezing into ice. This shift unleashed the most violent growth spurt in cosmic history, a period known as inflation. In a span of time almost too short to conceive, from 10 to the negative 36 to 10 to the negative 32 seconds, the cosmos expanded exponentially, doubling in size over and over again at a rate far beyond the speed of light. A region of space smaller than a single proton was stretched to a size larger than our entire observable universe today, all in a fraction of a blink of an eye. This idea, pioneered by physicist Alan Guth, solves profound puzzles about our universe. Why does the cosmos look so similar in all directions? A mystery called the horizon problem. Because it all originated from a tiny patch that inflated to become everything we see. Why is the universe so flat, meaning its geometry follows the rules of Euclid, a puzzle known as the flatness problem? Because inflation stretched it so enormously that any initial curvature was smoothed out to near perfection. The engine for this explosive growth was a strange new energy field that permeated the vacuum of space itself, a scalar field theorists call the inflaton. As this field descended to a lower energy state, it released a tremendous repulsive force, pushing the fabric of space-time apart with unimaginable vigor. This expansion did something truly magical to the microscopic quantum jitters left over from the Planck Epoch. It stretched those tiny, subatomic fluctuations to cosmic proportions, magnifying them into faint ripples in the density of matter and energy. These ripples became the cosmic blueprint, the gravitational seeds from which every galaxy, star, and ultimately every planet would one day grow. Inflation acted as a universal reset button, erasing any prior irregularities and creating a perfectly smooth and flat starting canvas for the hot Big Bang to come. But all growth must end. When the inflattened field finally settled into its lowest energy state, its vast potential energy had to go somewhere. That energy was dumped violently back into the universe, a process called reheating. In an instant, the cold, empty expanse of the inflating universe was flooded with a seething, hot plasma of fundamental particles, setting the stage for the next, equally dramatic act of creation. The universe was now reborn, hot and dense, ready to build the elements of reality itself. And with that, the cosmic reset was complete. The violent expansion of inflation ceased, but its end unleashed the next cataclysm. The immense energy that had been driving the inflattened field did not simply vanish. It decayed, flooding the cold, stretched emptiness with a seething, hot bath of particles and radiation in an event called reheating. In an instant, the universe was repopulated, transformed from a vast, cold vacuum into a dense, blindingly bright primordial soup known as the Quark-Gluon plasma. This was the true beginning of the hot Big Bang universe we recognize. The mechanism behind this rebirth is as complex as it is profound. The inflattened field did not fade quietly. It began to oscillate wildly, and through a process akin to a resonating spring, it efficiently transferred its energy into creating matter. This parametric resonance acted like a cosmic amplifier, pumping energy into the production of the universe's first fundamental particles. This newly forged plasma was unimaginably hot and dense, a chaotic sea where quarks and gluons, the building blocks of protons and neutrons, roamed freely without yet forming into the particles we know today. This state of extreme thermal equilibrium was absolutely critical. It meant that the temperature and density were uniform enough for predictable physics to take over. The conditions were now perfectly set for a sequence of events that would forge the first atomic nuclei from this raw, elemental chaos. The universe was no longer a cold, empty stage. It was a roaring furnace primed and ready for the creation of matter itself. This roaring furnace of a universe was a stage set for total annihilation. Within the seething Quark-Gluon plasma, a relentless drama played out. For every particle of matter created, an identical particle of antimatter was also born. These pairs were locked in a fatal dance, continuously colliding and obliterating each other in bursts of pure energy. If this perfect symmetry had held, the story would have ended right there. The universe would have been left as a fading, empty sea of light, devoid of stars, planets, or life. Yet we are here. A profound and mysterious asymmetry occurred, a 1 in a billion exception that made all the difference. This process, known as baryogenesis, is the reason our universe is filled with something rather than nothing. The Russian physicist and Nobel laureate Andrei Sakharov laid out the 3 essential ingredients required for matter to win this cosmic battle. First, there must be a violation of baryon number. A rule that seemed to decree the total amount of matter in the universe must remain constant. Somehow, that conservation had to be broken. Second, the universe needed to violate both charge conjugation and charge parity symmetry. In simpler terms, this means the laws of physics had to treat matter and antimatter slightly differently, creating a fundamental bias. Third, these processes had to occur out of thermal equilibrium, away from the perfect, symmetric heat of the primordial soup. Only under such shifting, non-steady conditions could a tiny preference for matter become locked in permanently. But what physical mechanism actually fulfilled these conditions? Why did matter receive this cosmic favor? this remains one of the most profound unsolved problems in all of physics. Experiments at facilities like the Large Hadron Collider are desperately searching for new particles or exotic interactions that could explain this overwhelming preference for existence. They are recreating the conditions of the early universe, hoping to catch a glimpse of the physics that saved us from oblivion. That one surviving particle in every billion annihilations does not sound like much, but it was everything. That delicate, almost negligible surplus of matter is the reason you, the Earth, and every galaxy you see in the night sky exist at all. It was the universe's first and most crucial investment, a tiny seed of substance that would one day blossom into the entire cosmic landscape. That one in a billion surplus of matter now found itself adrift in a seething ocean, the Quark Epoch. For the first microseconds of existence, from the end of inflation until about 1/1,000,000th of a second, the entire cosmos was this unimaginable substance, a Quark-Gluon plasma. This was not a universe of atoms or even of protons and neutrons. It was a primordial soup so hot and dense that the fundamental building blocks of matter, quarks and the gluons that carry the force between them, roamed completely free. They were like ingredients in a boiling pot, not yet baked into the stable particles that would form the bedrock of reality. We are not just theorizing about this state. Scientists at particle accelerators like the Large Hadron Collider have recreated tiny droplets of this quark-gluon plasma by smashing heavy ions together at nearly the speed of light. For a fleeting moment, they generate a fireball with temperatures exceeding several trillion degrees, allowing us to peer directly into the universe's first moments. In this extreme environment, a bizarre and counterintuitive phenomenon occurs, something called asymptotic freedom. The strong nuclear force, which is incredibly powerful at low energies, actually becomes weaker as the energy increases. At these astronomical temperatures, the quarks and gluons experience almost no resistance. They behave almost as free particles, their interactions growing faint in the intense heat. This is why they could exist in such a liberated, soupy state. Within this churning plasma, the universe was utterly opaque. Photons, the particles of light, could not travel any meaningful distance. They were constantly being scattered, absorbed, and re-emitted by the dense fog of charged particles. If you could somehow be there, you would see nothing but a blinding, featureless glow in every direction. But this chaotic freedom was destined to be short-lived. The universe was expanding relentlessly, and with that expansion came cooling. The energy of the particle soup steadily dropped. The Quark Epoch was a balancing act, a cosmic countdown. The moment the universe cooled below a certain critical threshold, a fundamental change became inevitable. The conditions were ripening for a dramatic phase transition, a cosmic lockdown that would bind quarks together permanently and forge the first permanent structures of matter. The cosmic lockdown began as the universe cooled past 1,000,000,000,000 degrees. The quark-gluon plasma, that sea of free roaming particles, had reached a critical threshold. In a phase transition as fundamental as steam condensing into water droplets, free quarks lost their independence. They were suddenly and permanently confined, bound together in groups of 2 or 3 by the unstoppable grip of the strong nuclear force. This process, known as hadronization, forged the very first complex particles in the cosmos, the hadrons. The most famous of these are the proton and the neutron, the future building blocks of every atomic nucleus in existence. This was not a peaceful birth. The universe remained a violent, high-energy battleground. Quarks and antiquarks continued their fatal dance of mutual annihilation, and in these first moments, the vast majority of matter and antimatter wiped each other out. But here, the 1 in a billion surplus from baryogenesis proved its worth. That tiny, inexplicable excess of matter quarks is the sole reason any protons or neutrons survived at all. Without that earlier cosmic bias, the universe would have been left with nothing but light. Yet, survival was not guaranteed. The newborn protons and neutrons were born into a furnace. The universe was still so immensely hot and dense that these particles were constantly slammed by high-energy photons and other particles. They were frequently blasted apart or transformed. A proton could be converted into a neutron and a neutron back into a proton through the actions of the weak nuclear force. This constant reshuffling meant the population of protons and neutrons was in a frantic, dynamic balance. Can you envision a universe where no structure was permanent, where the very particles that would one day form atoms were continuously created, destroyed, and morphed from one state to another? This was that reality. The establishment of protons and neutrons, even in this volatile state, was a monumental step. For the first time, the chaotic quark soup had coalesced into identifiable, stable structures with mass and identity. The universe was no longer a featureless primordial fog. It was now a dense, churning soup of hadrons, leptons like electrons, and blinding radiation, a chaotic but fertile ground from which the first atomic nuclei could finally emerge. As the universe expanded past its first second, a new light-filled era dawned. The chaotic hadron soup gave way to a realm dominated by ghostly particles called leptons. For the next 10 seconds, the cosmos was a brilliant, seething arena where electrons and their antimatter partners, positrons, were the undisputed stars. Energy remained so intense that pure light, in the form of colliding photons, could spontaneously transform into these particle pairs. The universe was a continuous, dazzling dance of creation and destruction, with electrons and positrons bursting into existence only to meet and annihilate back into pure energy a moment later. This frantic cycle maintained a perfect thermal equilibrium, meaning the radiation and the particles were locked in a searing, balanced embrace. Yet amidst this brilliant chaos, a profound liberation was occurring. Neutrinos, the most elusive and ghostly of leptons, finally broke free. For the first second, these particles had been trapped, constantly bumping into other matter in the dense plasma. But as the cosmos expanded and cooled, their moment arrived. Neutrinos interact only through the weak nuclear force and gravity, and around the 1 second mark, the universe became too diffuse for them to find partners. They decoupled, suddenly flying freely in all directions without another collision. This vast sea of liberated neutrinos still permeates the universe today, a fossil relic known as the cosmic neutrino background, an even more ancient cousin to the later cosmic microwave background. While this ghostly exodus was underway, a crucial shift was solidifying deep within the particle population. The frantic reshuffling between protons and neutrons, driven by the weak force, began to slow. As the temperature dropped, these interactions became less frequent, like a frantic game of musical chairs finally running out of energy. The ratio of neutrons to protons began to freeze, locking in a specific value. This was a pivotal moment. The final number of neutrons available would directly determine how much of the universe's primordial helium could be forged in the next few minutes. Without this freeze-out, the cosmos would have been left with far fewer of the stable nuclei essential for building stars and planets. Then, as the universe cooled further past the 10-second mark, the great electron-positron annihilation began. With insufficient energy to create new pairs, the vast majority of these particles met and obliterated each other. But thanks to the earlier matter-antimatter asymmetry, a tiny surplus of electrons remained, one for every proton in existence. This delicate balance of electric charge was the final gift of the Lepton epoch. the universe was no longer a blinding, opaque fireball of colliding particles. It had thinned and cooled just enough, its key ingredients measured and prepared. The stage was now set for the universe's first act of true alchemy, the forging of the first atomic nuclei from the primordial chaos. The universe was now cool enough for its first act of true alchemy. For a fleeting window from about 3 to 20 minutes after the Big Bang, the conditions were just right for nuclear fusion to begin. This period, known as Big Bang Nucleosynthesis, was the moment the chaotic particle soup began to organize into the first complex atomic nuclei. Locked in a frantic race against the universe's relentless expansion, protons and neutrons started to collide and stick. The first and simplest fusion created deuterium, a heavy isotope of hydrogen, by combining a single proton and a neutron. This was a fragile nucleus, easily shattered by the intense radiation still flooding the cosmos. But as the temperature dropped further, these deuterium nuclei became stable enough to serve as stepping stones. They quickly fused with more protons and neutrons, building the next elements on the periodic table. Helium-3, a light helium isotope with 2 protons and 1 neutron, formed. Then, 2 deuterium nuclei could collide to create the supremely stable helium-4 with 2 protons and 2 neutrons. This nucleus, also known as an alpha particle, became a cosmic vault, locking away nearly all the free neutrons that had survived the Lepton epoch. Trace amounts of lithium-7, the third element, were also forged, but the process slammed to a halt almost as soon as it began. The universe was expanding and cooling too rapidly. The density plummeted, and within minutes, the particles were too far apart and moving too slowly to overcome their mutual electrical repulsion. The fusion window closed, leaving behind a universe composed of about 75% hydrogen nuclei, 25% helium-4 nuclei, and minuscule amounts of deuterium, helium-3, and lithium. Why is this cosmic recipe so important? The predictions made by theorists for the abundances of these light elements are in stunning, precise agreement with what astronomers actually observe in the oldest, most pristine regions of space. This agreement is not a lucky guess. It is one of the strongest pillars of evidence for the entire Big Bang theory. The fact that we can calculate the helium content of a distant cloud of gas and have it match what our models say happened in the first 20 minutes is nothing short of breathtaking. It gives us tremendous confidence that we understand the universe back to this incredibly early epoch. With its fundamental chemical composition now locked in, the universe's work was done for a while. It had built the raw ingredients for everything to come, but the next great act of creation would require patience. The cosmos was about to enter a long, dark age, a silent expanse of hydrogen and helium gas, waiting in the darkness for the first stars to ignite. For nearly 400,000 years, the universe remained a searing, opaque fog. Then, a pivotal transformation unfolded as the cosmos cooled to a temperature comparable to a red giant star, around 3000 Kelvin. At this critical threshold, the energy of the raging radiation was no longer enough to tear atoms apart. Electrons, which had been roaming freely, were finally captured by atomic nuclei, primarily hydrogen and helium, in a serene process called recombination. This was the moment the universe became transparent. Before this, light was trapped. Photons could not travel any meaningful distance without scattering off a free electron, like headlights in a thick, blinding fog. With electrons now bound into neutral atoms, the fog lifted instantaneously. Photons were suddenly set free, streaming across the cosmos in every direction without interruption. This event, known as the moment of last scattering, released a flash of radiation that still fills the entire universe today. We observe it as the cosmic microwave background, a faint glow of microwave light that is the oldest picture we can ever see of our cosmos. This fossil light is not a random relic. It is a detailed snapshot of the infant universe, carrying within it the imprints of those tiny density fluctuations that were stretched to cosmic proportions during inflation. When we map the CMB with satellites like Planck and WMAP, we are reading the cosmic blueprint. The slightly hotter and colder spots in this microwave sky correspond directly to regions of slightly higher and lower density in the early plasma. These are the gravitational seeds from which everything would eventually grow. Every galaxy cluster, every swirling spiral of stars, and every solitary planet owes its existence to those faint ripples frozen in time. The release of the CMB marks a profound transition, the definitive end of the universe's primordial plasma phase. The era of building blocks was over. The cosmos entered a long, silent chapter known as the Dark Ages, filled with a vast sea of neutral hydrogen and helium gas and the fading afterglow of creation. For the first time, space was truly dark and clear, a silent stage awaiting the first actors. This cosmic background radiation is our most direct observational link to the universe's first seconds, a message from the dawn of time, encoded in light and delivered across 13.8 billion years. These silent dark ages were eventually broken by the first stars, but how can we be sure of what happened long before they ignited? We cannot travel back in time, yet we have built machines that allow us to recreate the universe's first moments. Giant particle accelerators, like the Large Hadron Collider at CERN, are our time machines. By smashing heavy ions together at 99.999991% of the speed of light, these colossal rings generate temperatures exceeding several trillion degrees. In the heart of these collisions, for a fleeting fraction of a second, a tiny droplet of the primordial Quark-Gluon plasma flickers back into existence. We are not just theorizing about the Quark Epoch anymore. We are observing it. Detectors surrounding the collision points capture the debris, allowing scientists to study the properties of this exotic state of matter. They have confirmed that at these extreme energies, quarks and gluons really do break free from their confinement, exactly as our models of the early universe predict. These experiments are not just recreating the past, they are actively searching for the future of physics. Colliders are hunting for new, exotic particles predicted by theories like supersymmetry, which proposes a shadow particle for every known particle we have. The discovery of such a particle could provide the missing mechanism for cosmic inflation, or finally explain the matter-antimatter asymmetry that made our existence possible. While these machines cannot reach the unimaginable energies of the Planck Epoch, they provide our most crucial windows into high-energy physics. Every single collision is a miniature Big Bang in a laboratory, a tiny fireball that lets us test the very laws that govern the universe's fiery infancy. The data streaming from these detectors is pushing the boundary of our knowledge ever closer to that first, unknowable instant, turning cosmic speculation into experimental science. While our cosmic story has focused on light and atoms, an even more ancient fossil permeates the void. Billions of neutrinos are streaming through your body every second, ghostly messengers from the universe's infancy. These nearly massless particles were forged in the first second, born from the violent interactions within the seething primordial soup. As the cosmos expanded past its first full second, something remarkable happened to them. The density of the universe dropped to a point where these neutrinos, which interact only through the weak nuclear force and gravity, simply stopped colliding with other matter. They decoupled, flying free on trajectories that have gone largely undisturbed for the past 13.8 billion years. This vast sea is known as the cosmic neutrino background, a relic that predates even the cosmic microwave background by hundreds of thousands of years. Think of it as the universe's first photograph, taken long before the flash of recombination that gave us the CMB. It is a snapshot of the cosmos at 1 second old, a time when the Lepton Epoch was ending and the fate of matter was being sealed. These particles hold direct, pristine information about that era, including the total density of the universe and the number of fundamental particle families. Most tantalizingly, they could reveal the precise hierarchy of neutrino masses, an ordering of their tiny masses that remains one of the biggest unsolved puzzles in particle physics. Yet, detecting this background is a monumental challenge. The expansion of the universe has stretched the wavelengths of these primordial neutrinos, cooling them to a temperature of just about 1.95 degrees above absolute zero. Their energy is now so incredibly low that they slip through almost any detector we can conceive. Current technology simply does not exist to observe them directly, as they are easily lost in the flood of higher energy neutrinos from the Sun, nuclear reactors, and cosmic rays. But their existence is a firm, non-negotiable prediction of the standard Big Bang model. Finding them would be like discovering a hidden chapter in a book we thought we had already read, offering a pure glimpse into a universe before atoms, before nuclei, when the first permanent structures were only just beginning to form. These silent witnesses hold the key to a time we can see in no other way, carrying secrets from the very edge of creation itself. That cosmic neutrino background is a relic of a time when the universe was already remarkably uniform. But this uniformity presents one of the most profound puzzles in cosmology. Why does the universe look the same in all directions? If you look at the cosmic microwave background, the temperature is identical to 1 part in 100,000, whether you look east, west, or at two completely opposite sides of the sky. This is the horizon problem. According to the standard Big Bang model without inflation, these regions on opposite horizons were never in contact. They were separated by a distance greater than light could have traveled in the age of the universe. How could they have possibly coordinated their temperature so perfectly? It is as if two people on opposite sides of the Earth, who have never met or communicated, decided to wear the exact same outfit down to the smallest detail. This should be impossible. The universe, it seemed, was breaking its own speed limit. Cosmic inflation provides the elegant solution. Before the inflationary burst, the entire patch of space that would become our observable universe was smaller than a single atom. This tiny region was causally connected, meaning every part of it was in thermal contact. It had time to even out its temperature and density, achieving a state of perfect equilibrium. Then inflation happened. That unimaginably rapid expansion did not just make the universe big. It stretched that tiny, homogeneously prepared patch to a size far larger than our entire observable cosmos today. Think of a single drop of food coloring perfectly mixed into a tiny vial of water. If you then pour that vial into an entire swimming pool, every part of the pool will have the same uniform pale color. The entire observable universe came from one tiny, well-mixed region. This is why the cosmic microwave background looks the same in every direction. The same initial conditions were imprinted everywhere because everywhere we look originated from the same microscopic starting point. Without inflation, the large-scale smoothness of the cosmos is a deep mystery. With it, the horizon problem vanishes. The solution is so powerful it directly ties the vast, macroscopic uniformity we see across billions of light years to the frenetic, microscopic quantum jitters of the universe's very first moment. This perfect uniformity is matched only by its perfect geometry. Our universe is flat. This is not a statement about planets or galaxies, but about the very fabric of space-time on the grandest scales. The angles of a triangle add up to exactly 180 degrees. Parallel lines never meet. The rules of geometry we learned in school, the Euclidean geometry that seems so intuitive, hold true across the entire cosmos. This simple fact is one of the most profound puzzles in cosmology. Why is the universe so geometrically perfect? This is the flatness problem. According to the original Big Bang model, the universe's curvature is a dynamic quality. A tiny deviation from perfect flatness in the first moments would not have remained tiny. It would have been wildly amplified over billions of years of expansion. For the universe to be as flat as we observe it today, its initial curvature at 1 second old had to be fine-tuned to an astonishing precision of 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. To put that inconceivable number in perspective, it is a level of precision far greater than balancing a pencil on its tip for billions of years. Without a mechanism to enforce this, the universe should have either collapsed back on itself in a big crunch almost immediately or expanded into a near-total vacuum long ago. The fact that we are here in a universe that has persisted for billions of years seems like a statistical miracle. Inflation is the mechanism that performs this miracle. The exponential stretching of space during that brief, violent burst acted like a cosmic iron. It smoothed out any primordial wrinkles or curves in the fabric of reality. Imagine the surface of a wrinkled raisin. Now inflate that raisin to the size of the entire Earth. From your perspective on the ground, its surface would appear perfectly, utterly flat. Inflation did this to our entire observable universe, stretching a potentially messy, curved micro-realm into the vast, flat macrocosmos we inhabit. This process drove the density of the universe incredibly close to the critical density, the precise balance point between expansion and gravitational collapse. The Planck satellite's exquisitely detailed map of the cosmic microwave background provides the definitive evidence. By measuring the size of the ripples in this ancient light, scientists have confirmed the universe's flatness to a remarkable accuracy of just 0.5%. This geometric perfection has a staggering implication for our ultimate fate. A flat universe is poised on a knife's edge, meaning it will continue to expand forever, gradually cooling and thinning out towards a silent, dark equilibrium. The inflationary paradigm elegantly explains why this fine-tuning is not a lucky accident, but a natural consequence of the universe's explosive birth. The geometry of everything we see was irrevocably set in that first, unimaginable fraction of a second. That same primordial forge that built the atoms in your body also created an invisible architect. Dark matter, the mysterious substance that outweighs all visible matter by a factor of 5 to 1, was likely born in the universe's first second. Its ghostly presence, felt only through its immense gravitational pull, dictates the formation and rotation of every galaxy. Yet we have never directly seen it. So what is it, and when did it emerge from the cosmic fire? The leading idea points to a thermal birth. In the unimaginably hot and dense plasma, ordinary particles were constantly colliding. Theories suggest that dark matter candidates with names like weakly interacting massive particles, or WIMP, were also created in this frenzy. These particles would have been interacting frequently, banging into others and maintaining a balance with the radiation bath. But as the universe expanded and cooled, a critical moment arrived. The temperature dropped below the mass of these WIMP. Suddenly, the particle soup became too thin and too low energy for them to find annihilation partners. They froze out, decoupling from the rest of the cosmic stew and leaving behind a permanent relic population. The density of this frozen-out dark matter, calculated from these models, aligns stunningly well with what we observe in the cosmos today. It is a compelling narrative, but it is not the only one. Other theories propose a non-thermal origin. Perhaps dark matter was not forged in the heat of the plasma, but was spun out directly during the violent process of reheating that ended inflation. Or maybe it is the decay product of an even more exotic primordial field that has long since vanished. The identity of dark matter is arguably the greatest outstanding mystery in modern physics. Its discovery would do more than just solve a cosmic puzzle. It would be a direct message from the universe's first instance, a fossil from an era we can never recreate. To catch this ghost, scientists have built exquisitely sensitive experiments. Detectors are placed deep underground, shielded by miles of rock from cosmic rays, waiting for the once-in-a-lifetime bump of a dark matter particle drifting through. Telescopes in space scan for the indirect signals of dark matter particles annihilating each other in the hearts of galaxies. Every search brings us closer to understanding not just what dark matter is, but the precise moment it began to shape our reality. Its silent, pervasive dominance is a ghostly echo from the universe's very first breath. Gravity itself was ringing like a bell, while inflation was stretching quantum jitters into the cosmic blueprint for galaxies. It was simultaneously performing another, even more profound act. It generated ripples in the very fabric of space-time, waves of gravity that have been streaming through the cosmos ever since. This is the primordial gravitational wave background, a predicted hum from the universe's violent birth. If the cosmic microwave background is the first picture of the infant cosmos, this gravitational echo would be its first sound. These waves are not made of matter or light. They are literal vibrations in the geometry of reality, stretches and compressions of space itself. Because they interact so weakly with matter, they have traveled for 13.8 billion years virtually unimpeded. They carry uncontaminated information, a pristine signal from the inflationary epoch that has not been scrambled or altered by the plasma, particles, and forces that came after. Detecting this signal would be the single most powerful confirmation of cosmic inflation, a smoking gun from the universe's first fraction of a second. The hunt is on, not by listening for a faint sound, but by looking for a unique signature imprinted on the oldest light we can see. As these primordial gravitational waves washed through the hot plasma just before recombination, they left a distinctive curl-like pattern, a specific type of polarization in the cosmic microwave background. It is like finding the fossilized footprints of a dinosaur in ancient mud. Experiments like the BICEP array at the South Pole are meticulously scanning the CMB, searching for this faint swirl pattern in the polarization of the ancient light. The next generation of missions, like the upcoming Light-Bird satellite, are designed with even greater sensitivity to find this elusive mark. The stakes could not be higher. The amplitude or strength of these gravitational waves is directly tied to the immense energy of the inflaton field that drove inflation. Measuring this signal would tell us the precise energy scale at which this explosive growth occurred. This is not just a test of inflation. It is a direct probe into the realm of grand unification, offering a glimpse of the physics that merged the fundamental forces when the universe was a trillionth of a second old. To hear this hum would be to eavesdrop on the moment the cosmos was born, a fundamental vibration that set everything in motion. This tiny, non-zero value of dark energy is the greatest mismatch between theory and observation in all of science. Quantum field theory, our most successful framework for describing particle physics, makes a startling prediction about the energy of empty space. It suggests that the vacuum should be seething with a tremendous energy density, a product of all the quantum fluctuations bubbling up and vanishing. The calculated value of this vacuum energy is a number so colossal it is almost meaningless. exceeding the observed value by a factor of 1 followed by 120 zeros. This is the cosmological constant problem in its raw form, a discrepancy so vast it points to a fundamental gap in our understanding of reality. How could the energy of the vacuum be so perfectly tuned to almost nothing? This value was not set yesterday. It is a relic, a fundamental parameter likely locked into the fabric of the cosmos during its first instance. Some physicists speculate that a mechanism during inflation, or a later phase transition in the universe's youth, dynamically adjusted this value, cancelling out the enormous quantum contribution to leave behind the faint whisper we detect today. It is as if a cosmic accountant performed a calculation with 120-digit numbers and arrived at a final balance of mere pennies. We have no idea what that accounting process could possibly be. The mystery deepens with a second, equally profound coincidence. We happen to live in the brief sliver of cosmic time, a window of a few billion years, where the energy densities of matter, radiation, and dark energy are all roughly comparable. For most of cosmic history, one component has overwhelmingly dominated, but right now, in our present era, they are of the same order of magnitude. This is statistically bizarre. Why now? This cosmic coincidence adds an anthropic dimension to the puzzle. Perhaps the value of the cosmological constant is not a unique number, but one of many possible values across a vast multiverse. In most of those universes, the constant is too large, causing space to expand so rapidly that no galaxies, stars, or planets ever form. We find ourselves in one of the rare, hospitable pockets where the value is just right for complexity and life to emerge. Solving this enigma may require a complete overhaul of physics, perhaps through ideas like the holographic principle, where our three-dimensional reality is a projection of information stored on a two-dimensional surface. The tiny push of dark energy is not just a curious feature of our modern universe. It is a direct message from the dawn of time, a number written into the cosmic code that determined everything from the largest structures to the possibility of our own existence. Cracking its meaning would bring us closer than ever to understanding why the universe is the way it is. The notion of an absolute beginning is a profound one, but what if the Big Bang was not the true start of everything? Cutting-edge theories like string theory invite us to consider a cosmos with a history that stretches back before time zero. In these models, our universe may be part of an endless cycle of cosmic death and rebirth. One compelling idea is the concept of a big bounce, where a previous universe contracted in a big crunch, only to rebound into the explosive expansion we call the Big Bang. This cyclical model suggests our entire cosmic history is just one turn of an eternal wheel, with no ultimate beginning or end. String theory, with its vision of tiny, vibrating strings as the fundamental constituents of reality, opens up even more radical possibilities. It proposes that our three-dimensional universe might be a membrane or brain floating within a higher dimensional space. In this ekpyrotic scenario, the Big Bang could have been triggered by a collision between our brain and another parallel universe. The colossal release of energy from such an impact would have perfectly mimicked the hot, dense state of the traditional Big Bang. Another string theory concept introduces a pre-Big Bang phase driven by a field called the dilaton. In this era, the universe could have undergone a period of slow, steady contraction before the dilaton field's energy caused a dramatic reversal into the expansion we observe. These are not just wild speculations, they are mathematically rigorous attempts to answer the most fundamental question of all: what, if anything, came before? They push the very definition of time, suggesting that what we perceive as the beginning of time may have been a transition from a previous physical state where the arrow of time pointed in a different direction. If any of these models are correct, then the universe's first second was not a creation from nothing, but a dramatic bridge from a prior cosmic epoch. Exploring these ideas forces a complete re-evaluation of creation itself, taking us to the very frontier of theoretical cosmology, where the nature of reality itself is up for debate. Our entire cosmic history might be just a single chapter in an infinitely vast library. The same mechanism of inflation that solved the horizon and flatness problems does not simply stop after creating our observable universe. Theoretical physics suggests that once inflation begins, it becomes eternal, continuously spawning new pocket universes in an unending cascade. This is the multiverse hypothesis, a breathtaking vision where our universe is merely one bubble in a frothing cosmic sea. Each of these bubbles could have formed with a different random set of physical laws and constants. The strength of gravity, the mass of an electron, even the number of spatial dimensions might be different in these other realms. In this grand picture, the fundamental parameters that make our universe suitable for life are not the result of miraculous fine-tuning. They are simply the local bylaws of our particular cosmic neighborhood, a random draw in an infinite lottery. This idea emerges naturally from the mathematics of inflationary cosmology and is further supported by the many possible solutions within string theory. The concept is profoundly controversial, primarily because these other universes would be forever beyond our observational reach, separated from us by an ever-expanding inflationary domain. Yet if this picture is true, the first second of our universe was not a unique beginning. It was a local event, a single bubble nucleating in an eternal, meta-stable landscape. Our Big Bang becomes our local genesis, while the greater meta-universe has no beginning and no end. This radically recontextualizes our place in existence. Every galaxy, every star, and every life form is part of a single story in a collection of stories so vast it defies comprehension. It challenges us to consider that the quest to understand our origin may be even grander and more humbling than we ever dared to believe. Our universe may have forgotten its own origin. Deep within the laws of physics lies a fundamental rule: information cannot be created or destroyed. It can only be transformed. Every particle, every force carries data about its history. Yet when we apply this quantum principle to the Big Bang, we confront a baffling paradox. The primordial singularity seemingly erased all information about its own state. Where did that data go? This is the cosmological information paradox, a puzzle that pits the bedrock of quantum mechanics against the story of our cosmic birth. If information is truly lost, our most fundamental understanding of reality is incomplete. The solution might be written into the very fabric of the cosmos we see today. Some physicists propose that the information was never truly destroyed. Instead, it was scrambled and imprinted into the intricate correlations between the particles and fields that burst forth after the Big Bang. The specific way particles are entangled with one another, the subtle patterns in the cosmic microwave background, even the large-scale structure of galaxies, could all be a complex code preserving the universe's initial conditions. This idea finds its ultimate expression in the holographic principle, a revolutionary concept born from the study of black holes. It suggests that all the information needed to describe a three-dimensional volume of space, like our entire observable universe, is actually stored on a two-dimensional surface at its boundary. For the cosmos, that boundary is the cosmological horizon, the ultimate edge of what we can ever see. In this view, the universe's first second was not an erasure, but a translation. The data of the singularity was projected like a hologram onto the surface of the newborn cosmos, encoding its past into the relationships that would shape its future. Solving this paradox is not merely an academic exercise. It is a crucial step toward a complete theory of quantum gravity, forcing us to weave the microscopic world of information with the macroscopic scale of the entire cosmos. The answer will require a radical new understanding of what space, time, and reality truly are, suggesting that the entire history of the universe was written in that first, fleeting instant. This fine-tuning of the cosmos is not a minor detail. The fundamental forces and constants of nature appear to have been calibrated with astonishing precision, set in stone during the universe's first second to make life possible. This observation is known as the Anthropic Principle. It confronts us with a startling idea that the properties of the universe are intimately connected to the existence of observers within it. Consider the strong nuclear force, the glue that holds atomic nuclei together. If it were just a few percent stronger, protons would bind so fiercely that all the hydrogen in the early universe would have fused into heavier elements. There would be no water, no long-lived stars like our Sun. If it were slightly weaker, protons could not stick together at all, preventing the formation of any elements besides hydrogen. The universe would be a sterile sea of the simplest atom, with no chemistry, no planets, and no one to ask why. The same delicate balance applies to the force of gravity. If gravity were significantly stronger, the universe would have collapsed back on itself in a fiery big crunch long before life could evolve. If it were much weaker, matter would never have clumped together to form the first stars and galaxies. We exist in a very narrow window of possibility, a razor's edge of physical law. So how did we get so lucky? One compelling answer lies in the multiverse. If our universe is just one bubble in an infinite, eternally inflating foam of universes, each with its own random set of physical constants, then our good fortune is an illusion. We could not possibly find ourselves in a universe that does not support life. We simply inhabit one of the rare, hospitable pockets where the numbers lined up just right. The alternative is even more profound. Perhaps there is no multiverse lottery. A deeper, unified theory of physics, a true theory of everything, might uniquely predict the constants we observe. In this view, the universe must be the way it is. There is no freedom, no chance, only mathematical necessity. The Anthropic Principle forces us to confront our own role in the cosmos. It suggests that the universe's capacity for self-awareness is not a random accident, but a fundamental feature written into the cosmic code from the very first moment. The fact that we can look back, decipher the clues from the first second, and ask these questions might be the most important part of the story. The universe became comprehensible because it was always meant to be understood. The answers to these ancient riddles may be closer than we think, arriving in a flood of data from a new generation of cosmic observatories. The James Webb Space Telescope is already peering into the era of the first stars and galaxies, seeing them not as they are today, but as they were over 13 billion years ago. By studying these infant structures, we gain indirect clues about the primordial density ripples that seeded them, allowing us to test the details of the inflationary blueprint. On the ground, the Vera C. Rubin Observatory will soon begin an unprecedented decade-long survey of the sky, mapping billions of galaxies to trace the invisible hand of dark matter with exquisite precision. Meanwhile, next-generation telescopes are being designed with one primary goal: to find the faint, swirling pattern in the cosmic microwave background that would be the definitive signature of primordial gravitational waves. Catching that signal is the holy grail of modern cosmology, a direct whisper from the inflationary epoch that would tell us the energy scale at which our universe was born. But our quest is not confined to the heavens. On Earth, physicists are planning colossal new particle colliders, machines that would dwarf the Large Hadron Collider. These behemoths could recreate conditions so extreme that they might produce the very particles responsible for dark matter, or finally reveal the mechanism behind the matter-antimatter asymmetry. In deep underground laboratories, ever more sensitive detectors stand ready to catch the first glimpse of a dark matter particle, a discovery that would instantly illuminate a hidden chapter of the first second. The synergy is breathtaking. A single measurement of a neutrino's absolute mass could reshape our understanding of the early universe's expansion and the formation of large-scale structure. A breakthrough in theoretical physics, such as a coherent model of quantum gravity, could finally allow us to peer past the veil of the Planck Epoch and describe the moment of Genesis itself. We are living in a golden age where the boundaries of our knowledge are being pushed back on all fronts. This grand collaboration between telescope, collider, and chalkboard is transforming our origin story from a collection of fascinating speculations into a precise empirical history. The journey to understand that first second is more than a scientific endeavor. It is one of humanity's greatest adventures, a testament to our unyielding desire to know where we came from and how our magnificent universe began. This cosmic story is far more than a collection of dates and data. It is a narrative that fundamentally reshapes our understanding of existence itself, challenging the very frameworks through which we view creation and our role within it. The idea of a definitive beginning, a singular moment in time, stands in stark contrast to many ancient creation myths that spoke of eternal cycles or gods sculpting the world from a pre-existing chaos. Our origin was not a gentle shaping, but a violent, mathematical genesis from a state that defies all human intuition. The concept of time itself transforms from an absolute river flowing from an infinite past into a property that emerged alongside space and matter, a shocking revelation that reconfigures our perception of reality. We are not placed upon a cosmic stage that was built for us. We are a fleeting part of the stage itself, an emergent property of its physical laws. This realization can be deeply disorienting, yet it is also a source of profound connection. Every atom in your body, from the oxygen in your lungs to the iron in your blood, was forged in the heart of a long-dead star. But the ingredients for those stars, the hydrogen and helium, were themselves created in the universe's first 20 minutes. You are not just in the universe is in you. This shared atomic heritage links every living person to each other and to the cosmos in a tangible, physical bond. With this knowledge comes a unique responsibility. Out of nearly 14 billion years of cosmic evolution, the universe has recently, on a tiny rock orbiting an average star, become conscious of itself. We are the universe's way of looking back and questioning its own origins. This self-awareness is not mentioned in the equations of physics, yet it is perhaps the most remarkable outcome of the entire cosmic process. It forces us to ask whether we are a glorious, isolated accident or if the universe is, in some deep sense, predisposed to eventually give rise to life and mind. There is no definitive answer, but the question itself reframes our search for meaning. Our purpose may not be written in the stars, but is instead something we create through our curiosity, our compassion, and our stewardship. This story of the first seconds is the shared inheritance of all humanity, a history that belongs equally to every culture and every individual. It reveals our existence as both recent and incredibly fragile when measured against the vast cosmic timeline. This perspective does not diminish us. It highlights the preciousness of our brief moment in the sun, fostering a profound appreciation for this pale blue dot and the intricate web of life it sustains against all odds. We often picture the Big Bang as a colossal explosion, a fireball erupting in a dark, empty void. But this mental image is profoundly misleading. The event was not an explosion in space. It was the explosive expansion of space itself. Think of the universe not as an object within a container, but as the container. At that first moment, all of space was everywhere at once, and it began stretching simultaneously from every point. This is why there is no center to the universe and no edge. Every galaxy is moving away from every other galaxy because the fabric between them is stretching, not because they are flying apart from a single blast point. The entire cosmos is the expanding remnant of that initial event. Another common mistake involves the singularity itself. We imagine it as a tiny, incredibly dense pellet sitting somewhere in the emptiness. But according to our best models, the singularity was not a location in space. It was a moment in time when the entire universe, all of space, and everything it would ever contain was compressed into an infinitely hot, dense state. There was no outside for it to be in. This leads to a crucial clarification about the Big Bang theory itself. It does not describe the absolute beginning of all things. The theory describes the earliest moments we can currently extrapolate backwards to using the known laws of physics, a hot, dense state from which the universe expanded and cooled into what we see today. What, if anything, came before that state is a frontier of active research, not a settled matter. The early universe was also far stranger than a simple fireball. It was a realm of pure, seething energy where the very concepts of particles and forces were transforming. The familiar building blocks of matter did not exist until the cosmos cooled enough for them to condense out of this primordial energy soup. By letting go of these misconceptions, we replace a simple but flawed picture with a far more wondrous and accurate reality. The true story of our cosmic dawn is not one of a bomb going off in the dark, but of space, time, and matter being born together in a single, breathtaking act of creation. That first second confronts us with the ultimate clash of titans. For a century, the two pillars of modern physics, quantum mechanics and general relativity, have described our world with stunning accuracy, yet they remain stubbornly incompatible. One governs the bizarre, probabilistic world of the ultra-small. The other dictates the elegant curvature of space-time on cosmic scales. Their union is the holy grail of physics, and the universe's explosive birth is the only laboratory extreme enough to test it. At the unimaginable densities of the Planck scale, the smooth, continuous geometry of Einstein's cosmos must shatter. It gives way to a seething, turbulent quantum foam, a probabilistic realm where spacetime itself loses its definition, bubbling with virtual particles and microscopic wormholes. This is not a gentle transition. It is a fundamental breakdown of our classical reality, forcing us to ask what space and time truly are at their most fundamental level. The quest to answer this has spawned two magnificent yet unproven frameworks. Loop quantum gravity proposes that space is not smooth, but woven from tiny, discrete loops, a fabric of finite threads. This vision naturally leads to a concept like the Big Bounce, where our universe was born from the collapse of a previous cosmos, avoiding a true singularity entirely. String theory, in contrast, suggests that the fundamental entities are not point particles but tiny, vibrating strings, and that our universe may be a three-dimensional membrane floating in a higher dimensional space. Each theory makes predictions about the early universe that could one day leave an imprint on observables like the cosmic microwave background. The very existence of our cosmic structure is a direct product of this quantum gravitational interplay. Those faint ripples in the early plasma, the seeds for every galaxy, were once microscopic quantum fluctuations. They were born from the violent marriage of quantum uncertainty and gravitational expansion, stretched to cosmic proportions during inflation. To resolve the tension between these two great theories is to seek a theory of everything, a single, elegant equation that could describe every force and every particle from the first moment to the present day. Cracking this code would not just complete a scientific quest, it would represent one of the crowning achievements of human thought, finally allowing us to read the universe's first and most fundamental line of code. This grand narrative of broken symmetries is the hidden engine of reality. From that initial state of perfect, featureless unity, our complex cosmos emerged through a sequence of cosmic cracks. Each time the universe cooled past a critical threshold, a fundamental symmetry was shattered, forever changing the rules of existence. The first and most profound break was gravity peeling away in the Planck Epoch. Then, during the grand unification epoch, the strong nuclear force split off, leaving the electromagnetic and weak forces still entwined in a final, elegant partnership known as the electroweak force. This state of symmetry meant that particles like the photon, which carries light, and the W and Z bosons, which mediate radioactive decay, were all massless and interchangeable. The universe was a place where light and the weak force were literally the same phenomenon, but this unity could not last. As the cosmos expanded and cooled further, it crossed another invisible line. The electroweak symmetry broke. In an instant, the photon remained the massless carrier of light and electromagnetism, while the W and Z bosons became immensely heavy, confining the weak force to an incredibly short range. This single event is why chemistry exists. It is why the sun shines through nuclear fusion, and why certain elements are stable while others decay. Without this breaking of symmetry, the universe would be a sea of massless particles interacting over infinite distances, a reality with no structure and no permanence. The mechanism behind this is believed to be the Higgs field. Think of the early universe as a crowded dinner party where everyone is standing, all equal and able to move freely. This is the symmetric state. As the room cools, an influential guest arrives and everyone naturally turns to face them, creating a preferred direction. This is symmetry breaking. The Higgs field is that influential presence. As it settled into its lowest energy state, it interacted with particles, giving some of them mass while leaving others, like the photon, untouched. This process released a tremendous amount of energy, potentially creating exotic relics like cosmic strings, theoretical flaws in space-time woven like cracks in ice. The entire evolution of the cosmos, from a unified superforce to the four distinct forces we know, is a story of sequential symmetry breaking. Each phase transition carved out a new set of physical laws, each crack in the perfect symmetry, introducing the diversity and structure that allowed for galaxies, planets, and life itself to eventually form. That faint, cold glow filling the void is our most direct window to the dawn of time. The cosmic microwave background is a time machine, capturing the universe as it was just 380,000 years after the Big Bang. While not from the very first second, this fossilized light is our single most powerful tool for deducing what occurred during that unimaginably early epoch. Its most striking feature is its profound uniformity. No matter which direction we look, the temperature of this background radiation is the same to within a tiny fraction of a degree. This near-perfect smoothness is a monumental piece of evidence for cosmic inflation, confirming that our entire observable universe was once a tiny, causally connected patch stretched to cosmic proportions. Yet, etched onto this uniform canvas are the most important marks in cosmic history: tiny anisotropies, fluctuations in temperature of just 1 part in 100,000. These are not random flaws. They are the amplified quantum fluctuations from the inflationary epoch, microscopic jitters stretched to macroscopic scales to become the gravitational seeds for all cosmic structure. Every galaxy and every cluster of galaxies we see today grew from these minute variations in density. By studying the subtle polarization patterns within this ancient light, scientists are conducting the most sensitive hunt imaginable. They are searching for the faint, swirling signature of primordial gravitational waves, the ripples in space-time from inflation itself. Finding that specific pattern would be the ultimate confirmation of the universe's violent birth. This relic radiation also acts as a precise cosmic ruler. It allows us to measure the fundamental parameters of our universe with breathtaking accuracy. From the CMB, we have determined the universe's age to be 13.8 billion years. We have confirmed its composition, finding that ordinary matter makes up only about 5%, with dark matter and dark energy constituting the rest. And we have verified its geometry, confirming that on the largest scales, the cosmos is flat. Spacecraft missions have progressively sharpened our view. The COBE satellite first detected the anisotropies, WMAP provided a more detailed map, and the Planck mission delivered the sharpest, most precise image of this infant universe we have ever seen. Analyzing the cosmic microwave background is the ultimate act of cosmic archaeology. We are not just looking at a picture, we are decoding a message, digging through layers of time to read the initial conditions set in the first fraction of a second. It is the closest we will ever come to staring directly into the universe's fiery cradle. Our journey ends where it began, with a cosmos smaller than an atom transforming into the vast expanse we call home. This hidden history reveals a universe born not in chaos, but from a state of profound simplicity and unimaginable energy. Within the blink of a cosmic eye, a series of precise, dramatic transformations unfolded. The mysterious singularity gave way to inflationary growth, stretching quantum jitters into a cosmic blueprint. The forging of matter from a seething plasma was decided by a 1 in a billion asymmetry, a fragile victory over total annihilation. Dark matter froze out to become the invisible architect of galaxies, while the fundamental constants were locked into values so fine-tuned that even a slight shift would have left the universe sterile and dark. This entire epoch, from the first separation of gravity to the release of the cosmic microwave background, is a story written in the language of physics. It is a narrative pieced together from the bold predictions of theorists and the painstaking observations of astronomers, connecting the bizarre quantum realm with the grand cosmic scale. We are not merely observers of this story, we are a product of it. The atoms in our bodies were forged in those first minutes, and the galaxies we gaze upon grew from those primordial seeds. This knowledge is more than a collection of facts. It is a source of awe, a reminder that our existence is woven into the very fabric of cosmic evolution. The universe's first moments are not a distant abstraction. They are the foundation of everything we are and everything we see. The quest to understand our origins continues, and each new discovery adds another line to this incredible story. If these profound ideas spark your curiosity, join us for more deep dives into the mysteries of the cosmos. We would love to hear which part of this cosmic journey resonated most with you, so feel free to share your thoughts in the comments below.